The National Electrical Code, or NEC, section 250.24. A5 states that the neutral conductor shall be bonded to the grounding electrode system at the service disconnect. NEC section 250.30. A1 states that a transfer switch shall be rated to carry the load that it serves and shall be equipped with a readily accessible means of switching between the normal supply and the alternate supply. NEC section 250.30. A2 states that the transfer switch shall be installed such that it will be accessible and protected against physical damage and tampering. Safety is a primary design consideration. Moving the neutral ground bond to the transfer switch ensures that the neutral and grounding systems are properly bonded in all operating modes, including generator backup. A circuit breaker on the normal side of the transfer switch provides protection for the transfer switch and the downstream distribution system in the event of a fault. Moving the bond and installing a circuit breaker at the transfer switch meets the requirements of NEC sections 250.24. A5 250.30, A1 and 250.30. A2. The owner's engineer may argue that a 4000 amp circuit breaker is not required as the transfer switch is only rated for 4000 amps. However, the circuit breaker provides protection for the downstream distribution system, not just the transfer switch. The owner's engineer may argue that the neutral ground bond should not be moved from the main switchboard. However, NEC section 250.24. A5 requires that the bond be located at the service disconnect, which is now the transfer switch. Based on the NEC requirements and design considerations, the recommended design is to move the neutral ground bond to the transfer switch and install a 4000 amp circuit breaker on the normal side of the transfer switch. This approach ensures safety, protection, and code compliance. The owner's engineer's concerns should be addressed by explaining the reasons for the design decisions and providing references to the applicable NEC requirements. The first consideration is safety. Ensuring a safe electrical system is paramount. Moving the neutral ground bond to the transfer switch guarantees that the neutral and grounding systems maintain proper bonding across all operational modes, including when the generator serves as the backup power source. This prevents potentially dangerous voltage differences and ensures a reliable path for fault current to return to the source, tripping over current protective devices and clearing faults quickly. Secondly, consider protection. Installing a circuit breaker on the normal side of the transfer switch is crucial for protecting both the transfer switch itself and the distribution system downstream. In the event of a fault condition, such as a short circuit or overload, the circuit breaker will promptly interrupt the flow of current, preventing damage to equipment and minimizing the risk of fire or electrical shock. The circuit breaker serves as a vital safety net, safeguarding the entire electrical system. Thirdly, focus on code compliance. Adhering to the NEC is not merely a matter of following regulations, it is essential for ensuring the safety and reliability of electrical installations. Moving the neutral ground bond and installing a circuit breaker at the transfer switch are specific measures that align with the requirements outlined in NEC sections 250.24, A5 250.30, A1 and 250.30, A2. These provisions are designed to ensure proper grounding, overcurrent protection, and safe operation of transfer switches and generator backup systems. Address the concerns of the owner's engineer by carefully explaining the rationale behind these design choices. The engineer might question the necessity of a 4000 amp circuit breaker, given that the transfer switch is also rated for 4000 amps. It is important to clarify that the circuit breaker's primary function is not solely to protect the transfer switch, but also to safeguard the entire downstream distribution system. In the event of a fault, the circuit breaker will trip, preventing the fault current from propagating throughout the system and causing further damage. Similarly, the engineer may express concerns about moving the neutral ground bond from the main switchboard. Explain that NEC section 250.24. A5 mandates that the bond be located at the service disconnect, which, in this case, is now the transfer switch. This ensures that the grounding system is properly established at the point where the electrical service enters the building, providing a solid reference point for voltage and preventing the build-up of stray currents. Providing clear and concise explanations, along with references to the relevant NEC sections, will help address the engineer's concerns and demonstrate the soundness of the proposed design. By prioritizing safety, protection, and code compliance, you can ensure a reliable and safe electrical system that meets the needs of the building and its occupants. Consider the load calculations. A detailed load calculation should be performed to determine the actual demand on the generator. This will help in selecting the appropriate size of the generator and the transfer switch. Oversizing the generator can lead to inefficiencies, while undersizing can result in overloading and potential damage. Consider the type of loads being served by the generator. Different types of loads, such as motors, lighting, and electronic equipment, have different starting and running current requirements. The generator and transfer switch must be sized to accommodate these requirements. Consider the available fault current at the service entrance. The circuit breaker on the normal side of the transfer switch must have a sufficient interrupting rating to handle the available fault current. This information can be obtained from the utility company. Consider the coordination of overcurrent protective devices. The circuit breaker on the normal side of the transfer switch should be coordinated with other overcurrent protective devices in the distribution system to ensure that faults are cleared selectively. This will minimize the extent of the outage and prevent unnecessary tripping of upstream breakers. Consider the impact of the generator on the building's grounding system. The generator must be properly grounded to ensure safety and prevent electrical noise. The grounding system should be designed in accordance with NEC requirement. Consider the maintenance requirements of the generator and transfer switch. Regular maintenance is essential to ensure the reliable operation of these components. A maintenance schedule should be established and followed. Consider the cost of the generator, transfer switch, and associated equipment. A cost-benefit analysis should be performed to determine the most cost-effective solution. Consider the long-term reliability of the generator and transfer switch. These components should be selected based on their reputation for reliability and durability. Consider the environmental impact of the generator. Generators can produce emissions that contribute to air pollution. The generator should be selected based on its emissions performance. Consider the noise level of the generator. Generators can be noisy, which can be a nuisance to building occupants and neighbors. The generator should be selected based on its noise level. Consider the availability of fuel for the generator. The generator must have a reliable source of fuel, such as natural gas, propane, or diesel. The fuel supply should be sufficient to power the generator for the duration of the anticipated outage. Consider the location of the generator. The generator should be located in a well-ventilated area that is protective from the elements. The location should also be easily accessible for maintenance and refueling. Consider the security of the generator. The generator should be protected from theft and vandalism. The location should be secured and access should be restricted to authorized personnel. Consider the permitting requirements for the generator. A permit may be required from the local authorities before installing the generator. Consider the insurance requirements for the generator. The building owner may be required to obtain insurance coverage for the generator. Consider the training requirements for operating the generator. Building personnel should be trained on how to operate and maintain the generator. Consider the emergency plan for the building. The emergency plan should include procedures for starting and stopping the generator, as well as for responding to power outages. The transfer switch is a critical component of a standby power system, allowing for the seamless transition between the normal power source and the generator. Understanding its operation and the relevant NEC requirements is crucial for ensuring a safe and reliable installation. The primary function of a transfer switch is to switch the load from the normal power source, typically the utility grid, to the alternate power source, which is usually a generator, and vice versa. This switching action can be performed manually or automatically, depending on the type of transfer switch. Manual transfer switches require a person to physically switch the load, while automatic transfer switches detect a power outage and automatically switch the load to the generator. The NEC provides specific guidelines for the installation and operation of transfer switches to ensure safety and prevent hazards. One of the most important requirements is proper grounding. The NEC mandates that the neutral conductor be bonded to the grounding electrode system at the service disconnect. In the context of a transfer switch, this means that the neutral ground bond must be located at the transfer switch itself, not at the main service entrance. This ensures that the grounding system is properly established regardless of whether the load is being supplied by the utility grid or the generator. Another key NEC requirement is overcurrent protection. The transfer switch must be protected by a circuit breaker or fuse that is sized appropriately for the load it is serving. This overcurrent protection device is intended to protect the transfer switch and the downstream distribution system from fault currents and overloads. The NEC also specifies requirements for the transfer switch's rating, accessibility, and protection against physical damage and tampering. The transfer switch must be rated to carry the full load it is intended to serve, and it must be readily accessible for inspection and maintenance. Additionally, the transfer switch must be protected from physical damage and tampering to prevent accidental or unauthorized operation. When selecting a transfer switch, it is important to consider the type of loads it will be serving. Different types of loads, such as motors, lighting, and electronic equipment, have different starting and running current requirements. The transfer switch must be sized to accommodate these requirements to prevent overloading and potential damage. It is also important to consider the transfer switch's switching characteristics. Some transfer switches switch the load instantaneously, while others have a time delay. The switching characteristics should be appropriate for the type of loads being served to prevent disruptions or damage. In addition to the NEC requirements, there are other design considerations to keep in mind when installing a transfer switch. These include the location of the transfer switch, the wiring methods, and the coordination with other electrical equipment. The transfer switch should be located in a dry, well-ventilated area that is easily accessible for maintenance. The wiring method should comply with the NEC and other applicable codes, and the transfer switch should be coordinated with other electrical equipment to ensure proper operation. Proper installation or maintenance of a transfer switch are essential for ensuring its reliable operation. The transfer switch should be installed by a qualified electrician in accordance with the NEC and other applicable codes. Regular maintenance, such as inspection, testing, and cleaning, should be performed to ensure that the transfer switch is in good working condition. Transfer switches are available in various configurations, including manual, automatic, and bypass isolation. Each type offers distinct features and benefits, catering to different application needs. Manual transfer switches are the simplest and most cost-effective option, requiring manual operation to switch between power sources. They are suitable for applications where power outages are infrequent and manual intervention is acceptable. Automatic transfer switches, or ATS, automatically detect power outages and seamlessly switch the load to the generator without any manual intervention. They are ideal for critical applications where uninterrupted power is essential, such as hospitals, data centers, and emergency services. Bypass isolation transfer switches provide an added layer of reliability by allowing the transfer switch to be bypassed for maintenance or repair without interrupting power to the load. They are commonly used in critical facilities where downtime is unacceptable. When selecting a transfer switch, consider the specific requirements of the application, including the load size, type of loads, switching speed, and level of automation. Also, factor in the cost, installation requirements, and maintenance needs. Proper grounding is crucial for ensuring the safety and reliability of a transfer switch installation. The NEC mandates that the neutral conductor be bonded to the grounding electrode system at the service disconnect, which, in the case of a transfer switch, is located at the transfer switch itself. This ensures that the grounding system is properly established regardless of the power source. In addition to the neutral ground bond, the transfer switch enclosure must also be properly grounded to provide a path for fault currents to return to the source. The grounding conductor must be sized according to the NEC and connected to a suitable grounding electrode system. Overcurrent protection is another essential safety measure for transfer switch installations. The transfer switch must be protected by a circuit breaker or fuse that is sized appropriately for the load it is serving. This overcurrent protection device is intended to protect the transfer switch and the downstream distribution system from fault currents and overloads. The circuit breaker or fuse must have a sufficient interrupting rating to handle the available fault current to the service entrance. Coordination of overcurrent protective devices is also important to ensure that faults are cleared selectively, minimizing the extent of the outage and preventing unnecessary tripping of upstream breakers. The NEC provides specific guidelines for the selection and coordination of overcurrent protective devices. Regular maintenance is essential for ensuring the reliable operation of a transfer switch. Maintenance tasks include inspection, testing, and cleaning. The transfer switch should be inspected regularly for signs of damage, wear, or corrosion. The electrical connection should be checked for tightness, and the mechanical components should be lubricated as needed. The transfer switch should also be tested periodically to verify its proper operation. This includes testing the switching mechanism, the overcurrent protection devices, and the grounding system. The transfer switch enclosure should be cleaned regularly to remove dust, dirt, and other contaminants. A clean transfer switch will operate more efficiently and reliably. Consider the specific needs of your facility and consult with a qualified electrician to determine the best solution. By following these guidelines, you can ensure a safe, reliable, and code-compliant transfer switch installation. Consider the long-term costs associated with owning and operating a generator and transfer switch. These costs include fuel, maintenance, and repairs. Consider the availability of qualified technicians to maintain and repair the generator and transfer switch. The availability of qualified technicians can affect the reliability and uptime of the system. Consider the impact of the generator on the environment. Generators can produce emissions that contribute to air pollution. Consider the potential for noise pollution from the generator. Generators can be noisy, which can be a nuisance to neighbors. Consider the security of the generator and transfer switch. These components should be protected from theft and vandalism. Consider the permitting requirements for the generator and transfer switch. A permit may be required from the local authorities before installing these components. Consider the insurance requirements for the generator and transfer switch. The building owner may be required to obtain insurance coverage for these components. Consider the training requirements for operating the generator and transfer switch. Building personnel should be trained on how to operate and maintain these components. Consider the emergency plan for the building. The emergency plan should include procedures for starting and stopping the generator, as well as for responding to power outages. Consider the potential for the generator to backfeed into the utility grid. Backfeeding can be dangerous and can damage equipment. The transfer switch should be designed to prevent backfeeding. The transfer switch should be listed by a recognized testing laboratory, such as Underwriters Laboratories, or all. Listing by a recognized testing laboratory indicates that the transfer switch has been tested and meets applicable safety standards. The transfer switch should be installed in accordance with the manufacturer's instructions. Following the manufacturer's instructions will ensure that the transfer switch is installed correctly and safely. The transfer switch should be inspected regularly for signs of damage or wear. Regular inspections can help to identify potential problems before they become serious. The transfer switch should be maintained in accordance with the manufacturer's recommendations. Proper maintenance will help to ensure that the transfer switch operates reliably for many years. The transfer switch should be tested periodically to verify that it is operating correctly. Periodic testing can help to identify potential problems before they cause a power outage. The transfer switch should be replaced if it is damaged or worn. Replacing a damaged or worn transfer switch can help to prevent a power outage. The transfer switch should be located in a dry, well-ventilated area. A dry, well-ventilated area will help to prevent corrosion and overheating. The transfer switch should be protected from physical damage. Protecting the transfer switch from physical damage will help to prevent it from being damaged or disabled. The transfer switch should be accessible for inspection and maintenance. Accessibility will make it easier to inspect and maintain the transfer switch. The transfer switch should be labeled clearly. Clear labeling will help to ensure that the transfer switch is operated correctly. The transfer switch should be included in the building's emergency plan. Including the transfer switch in the building's emergency plan will help to ensure that it is used correctly in the event of a power outage. The transfer switch should be connected to a reliable source of power. A reliable source of power will help to ensure that the generator starts and runs reliably. The transfer switch should be sized properly for the load that it will be serving. Proper sizing will help to prevent overloading and damage to the transfer switch. The transfer switch should be compatible with the generator that it will be used with. Compatibility will help to ensure that the generator and transfer switch operate correctly together. The transfer switch should be installed by a qualified electrician. A qualified electrician will have the knowledge and experience to install the transfer switch correctly and safely. The transfer switch should be inspected by a qualified electrician after it is installed. An inspection will help to ensure that the transfer switch is installed correctly and safely. The transfer switch should be maintained by a qualified electrician. Proper maintenance will help to ensure that the transfer switch operates reliably for many years. Consider the use of a surge protective device, or SPD, to protect the transfer switch from voltage surges. Voltage surges can damage electronic equipment, including transfer switches. An SPD can help to protect the transfer switch from damage caused by voltage surges. Consider the use of a power conditioner to improve the quality of the power supply to the transfer switch. Power conditioners can help to smooth out voltage fluctuations and reduce noise, which can improve the performance of the transfer switch. Consider the use of an uninterruptible power supply, or UPS, to provide backup power to the transfer switch in the event of a power outage. A UPS can provide backup power for a short period of time, which can be enough to allow the transfer switch to switch to the generator.